Here are some examples of truss structure A, B, C, and D. There are several methods of calculation of this truss model or truss design. They are Cremona diagram method, join method, Ritter method, and FEM or finite element method, stiffness matrix. The first three methods will have a calculation result of elements force, compression or tension, and support reaction. What about the finite element method? What the result of this calculation using this method? Let's see. When we using finite element method, we will have calculation result like element force and support reaction, same as the three method. But additional of this method will have a calculation result of displacement of each node. When we see, for example, this structure, we see there are many nodes of this structure. When we using this finite element method, we will know how each of this node will move. What is the displacement of this node? Let's see. Yeah. Here I show you as I have made a calculation with my application program. An example, I give a load on each node, and you can see the result, the displacement of the node. This is the normal structure, and when you give a load on this node, the structure will move. Each node will move and will result the displacement like this picture you can see. Also, there is remarks here. If the color like this color, you see, it means the element have a compression. When yellow or orange, yeah, right? Orange color, you may see this orange color or yellow or orange. This means this element suffering a tension. What about green? Green, it means the element have a zero stress or zero force. You see, this is green. And red, this is red element. It means this element suffering a buckling or fracture. This buckling or fracture, we will see next how the application can determine this is buckling of fracture. And if element with color blue, it means normal position or normal element without load or without stress. This is the normal position, the normal truss. Also in my application, I add some feature about how to check the buckling for compression, fracture for tension. Also in this application, I include the calculation of distribution load on an element and the self weight of each element. For example, if this in this structure, if we have a distribution load in this section or in this one element, we can give a distribution load here, and the calculation result will show how the displacement, how is the stress on this element due to impact of the distribution load here, and also the impact of self weight of all elements will impact the calculation result. Okay, this is the introduction. Now let's have a look the application that I have made or I have programmed in Microsoft Excel. Okay, this is the view of my application about various truss calculation using the FEM or FEA method. As we can see, there are some menus in this application. This is the shortcut to go to the input data related to the menus here, like nodes. When we click nodes, cursor will go to the nodes area. When we click number of element or node, then the cursor will go to this area, number of element and number of node. When we click support type, the cursor will go to this area, support type, and you can input the support type here. When we click the load on nodes, then the cursor will go to this area, load on node. Load on node, first we should choose the unit of measure. Just click here and you can choose the unit of measure like meganewton, kilonewton, newton, gibbs, or pound force. Okay, then next, when we have choose the unit of measure, and you can fill the load here in each node. And orange highlight here, this is the menus, the shortcut menus to go to the result of all calculation. Let's try to click node displacement. When I click this node displacement, you can see it will go to this area. The displacement of each node will show here. This is still empty because there is no data input. When we input the data, the calculation result will show here. The displacement, the support direction, or an incline support direction. If there is an incline support, the direction will show here. And the element force of each element of the truss will show here. Also, in the calculation result, we can see we can show the drawing or the picture of the result of the truss displacement here. Okay, now we go back to the top area, and we are gonna start to input data of an example of truss structure. Here is an example of truss structure. As we can see here, this is one example of truss structure. Actually, I made some example here. As we can see, there are some example I already made here for the truss structure. But in this session, I will explain for this simple structure, this example. In this example, we can see how many elements here. We can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the structure has 11 elements. And what about the node? 1, 2, 3, 4, 5, 6, 7. The structure has 7 nodes. Okay, we know that the structure has 11 elements and 7 nodes. Now we start to input the data of number of elements and the number of nodes we input here. So the number of elements is 11 and the number of nodes is 7. Next, we are going to input the support type of the structure. We go back to the example drawing. As we can see, there are 2 support type in the structure. It is in node 4, the support is pin, the support type is pin, and in node 7, the support type is roller angle with 30-degree angle. And the other node 1, 2, 3, 6, and 5 has no support. So for this node without support, we can input none. Okay, so we can input here the support type. As we know, in node 1 no support, so we can input no. And then, oh, wait a minute, I have to change the calculation options from manual to automatic. So this gonna change. This will automatically show, okay, show the number of node. Node 2 also there is no support here, so we enter in node 2, we enter node. Okay, node 3, node 6, node 5 also node. 3, 5, 6, 3 node, 5 node, 6 node. And for the node 4, the support type is pin, and node 7, the support type is roller angle with 30-degree. Node 4 is pin support. Node 7 is roller angle support with a degree of 30. Okay, we put here 30-degree. Okay, next we are going to input the load on each node. The example here, we have two node have load. Node 1, it has load in y direction and x direction here. Fy1 minus 15 kips kilopounds, and fx1 plus 10 kips. So we input here. Fx1 is plus 10, Fy1 is minus 15, and the unit of measure of the load is in kips. Okay, we continue with node 5. The load is in only in the x direction. Fx5 minus 10 kips. Fx5 minus 10. Okay. The load we already entered in the support type. Now we go here. There is an option here. Use the same cross-section area and modulus Young for all elements. Yes or no. This means if the all elements have the same properties, and we can choose yes here. Also, if you want to include the self-weight of all elements, we can choose yes, but in this example, I will choose no. I will not include the self-weight of element here. Okay, because we choose yes for the all element have the same properties, and we can enter here their properties. Modulus Young. Okay, we can see here in this example the modulus Young E in Newton per millimeter square, 295,000 Newton per millimeter square, 295,000, and also the area. Okay, area in millimeter square, 500. Area is in millimeter square, 500. Sorry. Okay, done. Now because we go to the element details. Okay, as we know, there are 11 elements here in the structure, but first we have to choose the coordinate system of each element. This element, what kind of coordinate system we want to put the data. Is it in polar coordinate or Cartesian coordinate? Let's say we choose the polar coordinate. Okay, when we choose polar coordinate, so we have to input the angle of the element and the length of the element. First we look the element 1. Element 1, it is from node 1 to node 4. The angle is 0 degree because it is in horizontal. From 1 to 4, the position is horizontal, so the angle is 0 degree and the length is 3 meters. So we can input here, angle is 0 degree, the length of element 1 is 3 meters. Okay, don't forget to put the unit of measure of the element in meters, 3 meters. Okay, next element number 2. Element 2, from node 1 to node 2. What is the angle of this element 2? The angle is we should measure the angle always from the x, or from the horizontal plane, the x plane, go to the element. What I mean like this, okay, the angle of this element 2 start from x plane, go to the element 2. Okay, so this is the angle we want to determine. What is the angle of element 2? We can use trigonometry to have the angle of this element 2. Here I already determine the angle and the length of each element from 1 to 11. Element 1 to 11. I already determined the angle and its length, like here. Element 2, the angle is 23.9625 degree, and its length is 3.28 meters. What about element 3? This element 3, from node 2 to node 4 is element 3. The angle for the element 3 is 270 degrees, and the length is 1.3 meters, 1.33 meters. Why 270 degree for this element 3? Because again we have to get the angle, to measure the angle, always start from x plane, this x plane, and then because of this element 3 is start from node 2 to node 4, so it start from up to down. Then the angle we can determine the angle like this. This is the angle for element 3. Stop here. Okay. Okay. So the angle of this element 3 start from this x plane, x in x direction, go to the element 3, rotate from this x, go to the element 3. So this angle is 270 degree for the element 3. Okay. Delete. Okay. Okay. So to short the time, I will not input one by one, but I already explained how to get the angle and the length of each element. So I will copy the data of angle and length of element here, also the area and young modulus. I copy and paste the data here. Okay, done. And next, for this each element, we should give information like this element 1. It start the corresponding node of this element. Element 1 start from node, what node? We can see here element 1 start from node 1 to 4. So we input here for the element 1 start from node 1 to node 4. Element 2 from node 1 to node 2. Element 3 from node 2 to node 4. We have element 3, 2 to 4, and so on until element 11. To short time again, I will copy the data from here, from to here. I copy here and I paste here. Okay. Okay, you can see how the parameter here change when we put the data here. There's a stiffness K1 to K11, then the displacement of the node, support reaction, stiffness matrix, and the deflection or the displacement in U and V direction. Okay, what else data? Okay, as we can see here, there is a distribution load on element 9. How do we put this distribution load on this application? Or we can go to the right. In this, here we can see there is an option, distribution load Q on related element or member. Do we want to include yes or no? We choose here yes. When we choose yes, this area will be in yellow highlight. The distribution load, it is on element 9. So we will input the data in element 9 for the distribution load, which is for this column Li and Lf. What is it? What is about Li and Lf? This is the mean of Li and Lf. Because this element 9 start from node 5 to node 6, so the start point of this distribution load start from here. This is I and N to this point or F point. So the Li, the length of the distance of the distant position of the distribution load start from 5 to here, I, which is the distance is Li 1 meter. So we put Li for this element is 1 meters, and LF from point on node 6 to here is 0.8 meters. So LF 0.8 meters. Don't forget to put the unit of measure here. For the Li and Lf, it is in meters. Next, we go to input the distribution load Q, Qi in x direction, Qi in y direction, Qf in x direction, and Qf in y direction. Let's see. Okay. First, Qi in x direction. This is the Qi. Okay, I will zoom. This is the Qi. Qi in x direction plus 5 kilonewton meter. So we put here Qx 5 kilonewton per meter. Don't forget to put the unit of measure kilonewton per meter. Okay, and Qiy, this is Qiy 9 minus 7 then Qfx, this is I point and this is F point. Qf, this is Qf minus 5 in x direction, and Qf in y direction. This is the Qf in y direction minus 10 kilonewton per meters. Okay, it's all done. What else? I think it's already done. All data have been input. Now, because all data have been input, so now we can go to the result of calculation. Just click here. We want to see the node displacement. Just click this short menus. Okay, when I click, it directly go to the displacement. Here the displacement I want to see the displacement in millimeters. What if I make it empty? If it's empty, then the result will also empty. If I choose in centimeters, so the displacement will show the result in centimeters. If I choose in millimeters, the displacement will show the unit of measure in millimeters. Also, in this result calculation, we will have the support reaction in kips, kilopounds. If you want to change it to kilonewton or to pound force, you can change it here. Kilopound, incline support reaction. Because we have a incline support, so the result of the incline support, the reaction of incline support, we can have the result. Here. Let's go see the incline support reaction. Go to the top. Sorry, not here, but in this example. You may see the incline support reaction and R lambda 7. Here is the result of R lambda 7, minus 16.74 kips. R lambda 7. And it consists of Rx7 and Ry7. Rx7 is here, Ry7 is here. So we have all the calculation result here. and also the elements, the force in each element. Also we can have here, this is the force of each element from element 1 to element 11. Okay. Okay. Here I choose, sorry, when we as we see the displacement, the result calculation already shown here. What about the drawing? Here there is an option for the drawing. Do we want to show the nodes displacement on drawing below? Yes or no? If we don't want to show the displacement, so we can choose no here. Then the drawing of the truss will be shown here. This is the normal position of the truss, because we choose no here. What if we choose yes? If we choose yes here, if we put yes here, we will see, it changed. It changed because we want to see the displacement. So when we put yes here, then the displacement node will be shown here. As we can see in this node 1, we can see the displacement here. As we can see the node, this is the normal position. When we have a load in our structure, this node will go or will shift to down here. How much the displacement of this node 1, we can see here. For the node 1, it goes on x direction 3.95 millimeters, and in y direction it goes down for minus 40.3 something millimeters. Okay, so we can have all the results here, the calculation result and also the drawing result. What if we change the load on this structure? Let's go to the top. Here we know the load in 15 minus 15 kips, 10 kips and minus 10 kips. What if we change this load minus 15, we change to minus 150, and this become 100 and this become minus 100. Let's try. Okay, we change this one from 10 to 100, this one from minus 15 to minus 150, and this one from minus 10 to minus 100 kips. Let's go see the change of the displacement and the change of the drawing. What is the result? Let's go, let's click here. Okay, we can see here, this is the displacement calculation result. This is the result of the change of the displacement of the structure. As we can see, when we increase the load in node 1, so the node will also displace with a greater displacement. As you can see here, the structure will be like this. And we also can see the color of this element. It has a meaning. When we see the color of child, this color, it means the element suffering a compression. So this element suffering a compression. For the orange color, this one, orange color, orange, it means this element suffering a tension. And the green color is a zero element. But in the structure, we can see that there is no zero element in the structure. But if it has zero element, so it will goes to the color green. And the color red means if this element suffering buckling or fracture, then the element will change to the red color. Here we're not checking the element or buckling or fracture, but we have an option here. Let's go to the right now, and here we can check is the element suffering a buckling or fracture. Here's the option. If you want to check element for buckling, so that we can choose TCR. Let's put TCR here. Well, there is an error here. Find error. Please change the unit of measure in cell C13. Let's go to the cell C13. Go to the top. C13. We should input here the inertia of the element. In this example, we put the inertia in millimeter to the power 4. Yes, millimeter to the power 4. It is 203,000. So we can input here 203,000. And then we go back to the check buckling. Just click here. Okay, it's no error now because we already input the data need for the inertia. Well, we can see here all compression element, they are suffering buckling. If we go to the drawing, well, we can see here this element has changed to the red color. So this element has a compression and all suffering a buckling. So the load increase is not safe because the structure will go fail, because after we check, the all compression element is buckling. Okay, we can also check the element not just for buckling but also for fracture. Fracture means will be applied to element with tension stress. Okay, I think it's enough what I have explained about my application. Hope you can understand, and if you like this application of program, if you want to use it, you can have it from the link I put below. in the comment below.